So we are glad to have Professor Sudip Garai as our speaker today. So Professor Garai did his undergrad from Shivri College under Bardhaman University. There are people from Vietnam, plus. And then he went to Essenbos Center in Kolkata for his integrated MSc PhD degree, where he worked with Professor Sandip Chakraborty. And from there, he went to the US in Notre Dame to work with Professor Balsara, who is a very famous jet simulation, MHD simulation person. So he was a postdoc there for 5 years. And from there, he went to Kasi in Korea. Then came back to India, was a faculty member at Gitown University for a couple of years before he joined either Kolkata, where he has been since then. So Professor Garai, as you can understand from his research experiences, is an expert on simulations of magnetohydrodynamic systems like around compact objects, accretion disks and jets and stuff. And beyond that, I mean, given that that is a big connection with this department, because there's a lot of people here who are working on related topics. In addition to that, there is a very unique connection of Professor Garai with this department. His PhD defense seminar was held in the head of the department's office in the ground floor, because at the time the HOD, Professor Shomak Raichandani, was the external expert in his PhD defense committee. So the talk was held there. I think SC ma'am and I were in the audience. We asked, sorry, because you don't work in Asia, you didn't get that was so they're not, since it was in the head's office, they're not very big audience. So I was there were some questions and that was answered and all those. So there's a whole interaction of the.
So then that's, I think that was the first defense in Presidency University Physics Department. I'm not sure even in Presidency.
But it was not like PhD from Presidency.
Some defense seminar that was held for the first time.
So that's a very unique thing. So I think after that day, this is the first time she came back. Yes. After 12 years and after gathering much more experience and expertise. So we are eager to hear from you today.
Thank you. So thank you very much for the nice introduction and your invitation, of course. So in today's presentation, I will mostly I'll mostly advertise the works of our group without going into too much technical details of any specific paper or any specific topic. So as you can see, it's numerical experiment. So numerical experiment word I'm using to represent numerical simulations, and I'll mostly show results of X-ray binaries. Okay, although many of the results can be applicable for AGNs also, AGNs or even neutron star or white dwarfs. So it's astrophysical flows around compact object and flow onto neutron star, white dwarf or black hole in AGNs or nova or in pulsars. So all those are basically flow, some amount of magnetized flow onto those. Okay, so here is my plan of presentation. So first we will talk about the motivation, why we are doing this thing, and then I'll give the very brief introduction of our numerical tool. So some not very technical, but some amount of details on the numerical simulation code that we have been developing in our group, and then application mostly focus on X-ray binaries. So since I am visiting here first time, so these are I just want to tell you a little bit about my research interests. So these are my research interests. Primarily, I work on primary research interests are computational physics and astrophysics. In computational physics, I'm interested in designing or assembling finite volume based algorithm for studying the fluid dynamics and the fluid dynamics is separate side. We need to gather radiative output because that's what we see. So along with the fluid dynamics, I'm also interested in designing Monte Carlo based algorithm for different radiative processes. For example, bremsstrahlung or synchrotron or Compton scattering between them. So these are on the computational physics side, and on astrophysics, in the primary application area is understanding the uh, fluid dynamics as well as the radiative properties of that fluid from matter around the central object around of high energy sources. I prefer to develop or co-develop simulation codes. I've gained significant experience on this, and these are a few applications that we have so far done. So interestingly, these algorithms which we are using, they are used by mathematicians, developed by mathematicians. They are used and developed by engineers, mechanical engineer, aeronautical engineer, electromagnetic, the electrical engineering people, as well as many physicists. So I had opportunity to work on some electromagnetic which is so it is so the person with whom I worked, he's from electrical engineering department. He's a very famous person. So so some of these algorithms we also used or co-developed with them. So solution of Maxwell's equation, which is the primary bread and butter for many electrical engineers. So there also we use this finite volume method, which is technically known as computational electrodynamics for them. Okay, so let's move on. So here are the motivation part. So we see lots of data. So electromagnetic data, gravitational wave data from region around compact stars, or from directly from the compact objects. Okay. So this is famous even her EHT collaboration image. So this has been taken in radio band, but we know that and they claim that this image is from the horizon. I mean, the length scale that they show, it shows that it's a horizon scale image. So from this horizon scale image, the radio image is what they are showing, but we also know that from this horizon scale image, very high energy X-rays to gamma ray emissions takes place. So the question is how the radiations are produced. Okay, so that is the question that we ask. Specifically, what determines this kind of shape? What kind of fluid flow is there, which is giving us exactly this kind of shape? Compact objects also produce ripples in space-time. Gravitational wave, we have seen this kind of image. There are so many images are now coming up. So these radiations basically tell us, so along with the gravitational wave, if there are matter present, okay, so for example, if neutron star and black hole is getting merged, so along with this kind of gravitational wave, we expect some sort of electromagnetic radiation also because of some fluid interaction of along in the strong gravity. So so the question that we try to answer is that what kind of fluid dynamics goes on there, what kind of physical information can we extract from this radiation, and how we can model those by doing some numerical experiment of fluid dynamics. So I will mostly talk about the X-ray bands, not the radio. So radio, I'm skipping for this presentation. So typical X-ray data that we see, that we observe using our telescope, are this kind of some noisy data. So time series data. We have some photon counts. These are light curves, which many of you all know. So this is pretty old light curve, but just using this, we can tell what kind of information we are. So how we can tell how this set of data actually motivate us to go deeper into the fluid dynamics. So when we have this kind of light curve, observationalists try to extract spectral property. They fit the spectral property with some theoretical models like black body, or they use quantization. So out of this entire spectrum, they fit the spectrum, some part with the black body part, some part with, so this is iron line, so some part using some Lorentzian, and then they use the power law model also. So these are all phenomenological models. Phenomenological models differ from the actual fluid dynamics solution. And so this is the spectral analysis that people do, and then they also do some temporal analysis. Temporal analysis takes us from the time series data to frequency domain data, where you see that this kind of time series data sometimes respect some oscillation which is going on there. So what is giving rise to this kind of oscillation? Can we reproduce this oscillation through some experiments? So those are the typical things that we try to address. Okay, so the spectral classes are also so the spectrum also changes from different objects. So here I have shown spectrum of this GRS 1915 plus 105. This is a famous X-ray binary which has been studied with RXT for quite a long time. So this object, for example, shows something which is known as hard state. It also shows soft state. So the spectral state changes. So when you say hard state, it means there are more photon on the high energy side. Okay, high energy side, number of photons in the high energy side is relatively more compared to a soft state spectrum. So what triggers this kind of state transition? I mean, definitely something is going on. It's the black hole is not changing, it's static there. So fluid is falling onto them, which is producing the radiation. So definitely something is going on into the fluid. So can we reproduce this kind of state transition through tuning something? So that's what we try to see. So it's not only GRS 1915 plus 105, Cygnus X1 and many other objects shows this kind of transitions. So here is a famous paper by Belloni, very well cited paper, which actually characterizes different states just within 1 year, 1996 to 1997. So many states are seen for this one single object. So what triggers it? So there are several black hole X-ray binaries which are being detected. This is a very old result, old compilation by Remillard and McClintock. Some updated information list is available here. So so all these objects shows lots of variability. I mean, sometimes they are in dim state, not detectable, then they suddenly go into outburst, and then they remain there in the outburst phase, and then they again dim. So what triggers those things? So typically for these X-ray binaries, our usual understanding or picturization is something like this. So we most of the time, I mean, so what happens is that most of the cases we believe that there is a black hole sitting. So there is a binary which one is the black hole, the one component is black hole, the other component is some star. So it may be high mass star, high mass with respect to this, or maybe low mass. So low mass X-ray binary, high mass X-ray binary. These are the terminologies that we frequently use, and we believe that from this star, matter is either by tidal disruption event or by activity of this star, maybe flaring activity or wind, etc. Matter transfer from this we call this a secondary object, from the secondary to the primary black hole, and then the black matter, because angular momentum conservation is required to maintain, so matter actually spirals around it, and during the spiraling, we believe angular momentum has to be transported, so some viscosity is present, and that viscous force actually allows to slowly spiral. It may happen that if the matter is not so the infalling matter, if the infalling matter doesn't have sufficient angular momentum, or if it is nearly free falling, which may be the case if wind is significant amount of wind is getting ejected from this star, then they may be nearly free falling. They may not pass through L1 Lagrange point, but through other L2 or L3 Lagrange point. That in those cases, the accretion disk structure may be very tiny, and viscosity may not be that much important also. Okay, because they are nearly free falling. So in any way, some sort of accretion disk we believe is falling. It's not fully free falling. If it is fully free falling, then radiative inefficiency would be very less. Okay, so most of the energy will be purely advected. So it's not the case when we are seeing radiation means they are radiatively efficient. So if radiatively efficient disk, there has to be some mechanism that the radiation, there has to be certain time scale and also mechanism that radiation gets enough time to get out from the system. It's not goes into the black hole. So we believe that some sort of accretion disk formation is going on around this object, which actually allow the efficient emission of radiation, and not only radiation, some matter also gets emitted from this thing. So the jets are seen for many objects, and jets also carry lots of information about the inner part. Okay? So we will try to see if we can simulate the fluid dynamics, the radiative properties, the jet, all of these from single framework, because they are not isolated. All of them are connected. I mean, whichever accretion disk is producing the radiation, the same accretion disk configuration should also produce the jet. Okay, so we try to see, we try to investigate whether a single simulation framework can be designed. The same framework can, by tuning some parameter, whether the outburst can be reproduced, the spectral transition, hard state to soft state, which particular parameter tuning can give rise to those kind of state transition. So those and the correlation. So spectrally hard state shows lots of jet, whereas the soft state doesn't have jet. Whether this kind of correlation can also be reproduced from single simulation framework. So those are the things that we try to basically extract. Those are the things that we try to basically model from our simulation. So let me talk about a little bit about the accretion disk. So our general perception of accretion disk is something like this, that so if it is, so most of the time the black hole has spin. So there is very rarely any star which is not rotating or spinning. Even sun has a spin, right? So so if the stars, progenitor stars, so black holes form from some progenitor star. And if the progenitor star is rotating, then it will maintain its angular momentum, its angular momentum conservation. So when it shrinks and form the black hole, so that angular momentum will remain with the star. So most of the cases, we believe the central black hole is rotating. Sometimes we approximate Schwarzschild type black hole where we say the black hole spin is 0. So in those cases, what we mean is that the spin is less compared to the disk. So disk is also rotating and the black hole is also rotating. So there one can draw some sort of comparison. What is the spin angular momentum and the angular momentum of the disk? So you can do a comparative statement. So if you say that the spin is less for the black hole compared to disk, you can approximate it as Schwarzschild black hole. But it's very rarely case that a star or black hole has no spin. Okay? Now the disk rotation can be in the same direction as the black hole. Okay, in which case we say prograde rotation. So and in the other case we say the disk is rotating in a retrograde. It may also happen that they are not, the angular momentum are not aligned always in the same direction. It can also happen that disk and the disk angular momentum, on an average the disk angular momentum and the black hole angular momentum are misaligned. So that kind of situation can also happen. So if there are accretion disks very close to the black hole, then we know from some basic fluid dynamics that the accretion flow has to be transiting, because close to the horizon we say that matter enters with speed of light, whereas the ideal equation of state says that the sound speed cannot be equal to speed of light, but less. So matter Mach number far away from the black hole, fluid Mach number is less than 1. Mach number is defined as fluid velocity divided by sound speed. So sound speed very high away, very far away from the black hole, the velocity of the matter is very less, sound speed is somewhat high, so flow is subsonic, and as it comes close to the black hole, its speed increases. So so fluid velocity keeps on increasing, sound speed also keeps on increasing, but at least close to the black hole when it entering, there the flow has to be supersonic. So we say that accretion is necessarily a transonic event, and from this kind of transonic disk, gravitational energy release is the primary source of radiation. Okay, so we can understand, we can justify this sentence just by doing some simple calculation in just interest. I mean, we can very easily calculate the energy release for 1 gram of matter falling from infinity to horizon. So that you can calculate, it will come out to be 10 to the power 20 arc per gram. Okay, whereas in fusion, where hydrogen to helium takes place, the emission is around 10 to the power 18 arc per gram. So at least 2 order of magnitude high energy we see. So this black hole, so the accretion disk around the compact objects are most of the time are very luminous because of this gravitational energy release. Okay. So what are the type of equations that can describe this fluid dynamics? Okay, so these are the only a few slides of equations. Other than that, we will not show much equation. So so fluid dynamic equations are something which we study in our undergraduate. So they represent mass conservation, momentum conservation, and energy conservation. So this is known as simple hydrodynamic equation. So hydrodynamic equations are frequently used to model this kind of astrophysical flows. Okay, when magnetic field is comparatively weak. Okay, if magnetic field, if people, there are some groups which may believe, and it is true, that magnetic field is important in some cases. So then, in those cases, these equations are modified to give some provision of magnetic field, and we call these imaged equations. So where the mass conservation remains same, magnetic field affects the momentum equation. So magnetic field somehow carry angular momentum. It can help in transporting angular momentum, and the energy conservation equation also gets modified by introduction of magnetic energy. Situation becomes a little bit complicated by introduction of one additional equation, which is the Faraday's law. Okay, so Faraday's law del B del T is equal to curl of E. So where E is equal to V cross B, we are in, this is Ohm's law. E is equal to V cross B, which is used over here. So complexity increases if we want to bring in additional physics. Okay, situation can also be a little bit more complex if we want to retain. If we say that no MHD is not well justified, we need fluids. So mostly the fluid is plasma. So electron and ions are there. So there are people who may say that instead of single fluid assumption, we want to retain the electrons identity separately and ions identity separately. So then we can talk about electron temperature. What is the electron temperature in the cloud? Many times we extract the electron's temperature. Okay, so in those cases, we can bring in a little more complication. We can say we want to do electron positron, electron proton to fluid electrodynamics. In which case, the electrons fluid dynamic equation. So this is these equations are satisfied by both species. So electron species will satisfy the full set of fluid dynamic equation. Ion species will satisfy the full set of fluid dynamic equations, and they are connected by this full set of Maxwell's equations, where the current density is contributed by both electron and ions, and the charge density is contributed both by electrons and ion. Okay, and then they interact. One may additionally introduce some sort of frictional term between them. I have not shown them, but it's possible. Okay, so this is also some type of equation that we may time to time need to invoke in some cases, specifically for neutrons or magnetosphere. This type of equations are extremely close to the black hole. This type of equation may be of great interest, although the event horizon group did not use this equation while modeling their emission. They just use ideal MHD. Okay. And some more complexity, one may say that the generativity is not there. So what is the effect of generativity? So we can introduce generativity. We can write all the fluid dynamics equation by incorporating space-time metric. So this is the equations of generativistic hydrodynamics. One can do generativistic magnetohydrodynamics, and then one can go ahead and do generativistic two fluid electrodynamics. Okay, so these are different type of, and on top of these, one can introduce the dissipative processes. So for example, viscosity or radiative cooling, radiation pressure. So we can think of different type of physical processes and try to introduce those equations. Okay, and we should have technology or technique to address those. Okay. So here I am not showing the viscosity, but so I am showing only the ideal.
Here is that the V or
so this velocity is velocity.
Yes. That V dot V is also right.
Yes. So
these are all ideal.
So I'm showing ideal, but you can introduce cooling and viscosity also additionally.
Yeah. I just initially somehow thought that was a new.
Achha, no. So these are all velocity, same velocity.
Right. Yeah. Right.
So in our group, we basically try to develop solution for these different type of PD systems, partial differential equation systems, and the systems that we use are very general. I mean, they are used by mathematicians, engineers, astrophysicists. So they find application in different branches. So whenever we get some set of equations, so there may be different set of equations. I just showed you a few examples. We first perform some sort of characterization. So if you notice carefully, all the equations can be written in this general form. So where we have del t, time derivative of something, and then spatial derivative of some quantity, and then on the right hand side something. So we write characteristics matrix, and then we perform some sort of characterization. So we look at the eigenvalues and eigenvectors of those characteristic matrix and try to categorize whether the set of equations that I'm working with, they are hyperbolic, or they are parabolic, or they are elliptic. So why we do these things? Because there are plenty of techniques or algorithms available for different class of PD systems. Okay, hyperbolic has their own, parabolic have their own, elliptic have their own. So parabolic, elliptic, these equations are also familiar to you. I mean, heat conduction equation, give one example where conduction, elliptic terms, right? So the viscosity, okay, viscosity also it can be characterized. So once we know what type of terms we have, then accordingly we actually take or invent some technique for handling those kind of terms, and then all the different type of methods are combined, and a suitable scheme is developed. So here I'll go very briefly about the finite volume method. So in finite volume method, what we do is that the differential equation is written into a integral form, and then further this integral form is discretized, and then these type of evolution scheme is what we develop. And of course, there are lots of mathematical technique behind it, how the fluxes are calculated, what kind of solution. So these volumes are typically of Rg cube, Schwarzschild radius cube. One Schwarzschild radius for stellar mass black hole is around 30 kilometers. So within the 30 kilometer volume, the fluid variables actually change. I mean, their spatial variations should matter. Okay, so how those spatial variations are taken care of. So those are all mathematical details which are hiding behind this code development. Okay, so I do not talk about those things here. Just to show you, give you the feelings, I just show you the structure. Okay, and then of course, what kind of volume can we choose? So as we said that we in a finite volume method we discretize the equation on volume. So the volumes may be Cartesian type, or they may be logically rectangular mesh like cylindrical or spherical polar coordinate system. One can also assume a different type of meshing also. I mean, this is the typical spherical polar coordinate mesh, and you can see that this this two-dimensional surface, the difference between this two-dimensional surface and this two-dimensional surface. So here you can see there is a well-defined pole where lots of congestion is there, whereas this two-dimensional surface, two-dimensional spherical surface, is completely free of any singularity. Okay, so many times we perform fluid dynamic simulation on this kind of mesh. This kind of mesh becomes very suitable specifically when there is misaligned disk. So this angular momentum has its own axis, and the black hole angular momentum may have its own axis. So we do not give any preference to any axis. So this mesh, for example, doesn't give any preference to any particular axis. So you can choose any alignment, and then you just evolve your fluid dynamic equation, and then this kind of mesh we believe will give much better result compared to this kind of mesh. Okay, so so we are basically in process of designing our generativistic fluid dynamic simulation on this thing. Okay, and then comes the simulation time. Simulation time is also important for us. So there are simulations which can go for weeks to months if we just run them on serial mode. Okay, so we many times parallelize the code. So we frequently employ domain decomposition, and we demonstrate that our codes are scalable. So here are some scalability tests that we have shown. So this scalability test I performed when I was a postdoc in USA with Dinsa Balsara. So here we performed scalability study of geodesic mesh. So the mesh that I showed in the previous slides, which is singularity free, those mesh are called geodesic mesh. So geodesic mesh code, which has been tested for scalability up to 80,000 processors, and this is another code which I wrote for fluid dynamics and cylindrical coordinate, and this scalability study has been performed in South Korea supercomputer after I came back to India. So when we develop some parallel algorithm, we also need to develop that. We also need to demonstrate that they actually scale up to very high processors. Okay, so these are all about codes. Now let us see some applications. Okay, so as I mentioned, I will mostly be talking about accretion disk, about binary X-ray binaries, accretion disk for X-ray binaries, but the simulation result that I'm going to show, they can easily be used to interpret the accretion flow around AGNs as well, because AGNs or pulsars or nova, so if we focus close to the central object, the structure is roughly same. Okay, so there is an accretion disk. So if we zoom the closed-in region, we basically model the closed-in region in a as a cylinder, where the disk the disk structure has a cylindrical symmetry. So mostly the cylindrical symmetry or spherical symmetry is what we mostly use. So we assume in our simulation there is a black hole sitting at the origin. So if it is RZ plane, then at r equal to 0, the black hole is sitting, and matter is coming from certain r. So as you can see here, it's an accretion disk. So matter is coming from a binary system. Matter is coming from the binary object. So we simulate most of the cases where matter is coming from far away, and then from the upper and lower boundary of our cylindrical domain, we allow matter to get out, just to model jet emission. Okay. So this is the typical simulation picture that we assume. And then here is one simulation, three-dimensional simulation of a thick accretion disk, which is on non-rotating black hole. So we have simulated a case where matter is coming from this side. So color basically shows you the density. Okay, so matter is coming from this side and it's falling onto the central black hole. And this simulation basically shows how toroidal thick corona can be formed around a black hole, and in subsequent results I'll show that this kind of toroidal disk, from this kind of toroidal disk in the vertical direction, outflow or jet can also get emitted. And as you can see, our simulation demonstrates that this kind of disk or the corona is highly variable. So we believe that if we tune the inflow properties properly, then we can tune the variability as well. Okay, so some sort of tuning of the flow properties, viscosity or cooling or magnetic field can give us the observed variability in the light curves that that our telescopes are visualizing. So just like an experiment, in any experiment we basically tune certain thing, right? So here also we can tune, so all the parameters, so there are, you can invoke the parameters and the parameters control is on you, and if you wish to reproduce something, then you can basically control those
So
things.
you are calling the relatively denser part the disk and the yellow low dense part the corona, or what? Which one are you calling?
No, so disk, so the entire matter, so as I showed you in the previous slide, so it is a cylindrical structure.
Right.
So the matter itself is the disk. Okay, matter itself is the disk, but the matter as it comes close to the black hole, it becomes somehow thicker. So in this case, because of centrifugal force which is trying to stop, the density has increased. So this entire this red to yellow region is the denser region, which I am calling corona. Okay, and the disk is this entire thing, including this one. So we do not separate out corona or disk or something. The entire thing is disk for me. Okay, so some part is high density, some part is low density. That's what is. I mean, we cannot separate out.
Here it's the part.
Of course, no. This part is hollow. So all the jet that we are simulating in these cases, they are hollow in nature, because angular momentum conservation is there, so matter cannot go very close to the black hole. So we see hollow jet. So this white part doesn't have any matter. The white part is matterless. So jet is mostly from this region.
You mean the
Okay.
boundary of the white part?
The boundary. So boundary part. So this part. So matter. I have not shown the velocity vectors. I will show you later. You will see that velocity vector in these regions are mostly outward. So wind, jet, everything is present. Okay. Okay. So here is another simulation where we see where we show that these accretion disks, when viewed from top, can actually show us some non-axisymmetric crescent-like structure. So crescent-like structure is what is observed in Event Horizon Telescope image, right? So those kind of spiral structure can also be simulated by tuning something. In this case, we basically perturbed the accretion disk. So the accretion disk had some beautiful, nice axisymmetric structure. This is the same accretion disk which I showed in the previous case. Okay, but if we just perturb the accretion disk by introducing some density perturbation, so here you can see that some high density got advected into this, and there are some paper which actually talks about the perturbation analysis of this kind of thing. But numerical simulation actually shows us that that kind of perturbation gives rise to non-axisymmetric structure, and this kind of perturbation can be naturally, enter into the simulation into a realistic configuration by non-local radiative cooling or non-local viscosity enhancement. Magnetic field may not be homogeneous; it may have inhomogeneity. So different place, the transport may be different. So inhomogeneity is part of this accretion business. So by introducing some sort of non-homogeneity, we are actually able to get the non-axisymmetric structure. Okay. So here is another simulation which shows the jet formation. So here we particularly focus on the long distance movement of the jet. So we purposely chose a simulation domain which is vertically elongated. Okay, so you can see the matter is coming and it formed the corona, the higher density jet, higher density inner part, and then from this inner part matter starts moving vertically upward and downward, and we believe so some part of the matter achieves, so here the velocity profile of this matter is shown as a function of distance. So we see that matter starts from very close to the black hole and they initially accelerates and then finally they achieve some sort of terminal speed. So these are purely hydrodynamic simulation. There is no magnetic field. So they are getting some initial push from the central location, which is giving them the initial acceleration. And then after they move out from the central closed region, there is no more force which is actually pushing them upward. So they are basically achieving a terminal velocity. But if there are mechanism, so for example, in many magnetohydrodynamic simulation, you can see the jets extending and accelerating also at very far out. So there must be some mechanism away from the black hole which should accelerate them. So in this case, those mechanisms are absent. So in this experiment, we did not include this. So but this simulation demonstrated that even without magnetic field, just by the centrifugal force and the pressure gradient force, matter can be thrown out and they can achieve pretty high velocity. So in this case, we got 0.15 of speed of light for the outflowing matter. Okay. We have also simulated case where we have included magnetic field in this kind of configuration. So here I'm showing you some experiment where we basically send in magnetic flux tubes, so along with matter. So for example, from sun, you can think that you know that several CMEs, when the plasma goes out from the sun, they basically take some flux tubes along with them, right? So similar case may also be happening in X-ray binaries. So X-ray binary has a companion star which is lots of dynamics. So from there, when some plasma is coming, they can bring in some frozen in magnetic flux tube along with them. So we have picturized that kind of configuration, and you can see that time to time some flux tubes or flux ropes are coming in close to the central region. So this shows the density and velocity vector. And if those kind of flux ropes are coming in, they for momentarily some time they actually disturb this region. Lots of outflow gets emitted from this region. This part becomes very dynamic, right? So so this kind of experiment we have also conducted. We have analyzed some of the cases, and we find that when the flux tubes arrive close to the black hole, they try to escape in the vertical direction. And while they try, so these are the snapshots at different successive times. So this is in Rg by C unit. So Schwarzschild radius divided by C. So you can convert this. For 10 solar mass black hole, this Rg by C is around 10 to the power minus 4 second. So this simulation shows around 1.8 second. All are 1.8 second, but the fourth decimal place is changing. Okay. So as the flux tubes is entering, they try to escape in the vertical direction, and while so colloidal field gets developed, and at the same time lots of matter also emit in this direction. Okay, so here are some simulations from the general relativistic hydrodynamic case. So in this case, I'm showing a simulation onto a non-rotating black hole. So onto non-rotating. So these are the 2D snapshot of the same 3D simulation. So in this case, I'm showing you the structure of the torus, which is getting formed, which is getting formed around the black hole. Okay, so
so what is collimating that outflow? Is that the shape of the toroidal shape of the inflow that is collimating the outflow, or
there is, so in this case the magnetic field is absent. Okay, so what is happening is that the matter which is getting injected, they have certain thickness, and as they are coming, the gravity is pulling it off. Okay, so here the centrifugal force and the centrifugal force is acting outward, gravity is pulling inward, so there is a tug of war, because of which matter is getting slowed down over here. And after, some sort of shock or centrifugal barrier forms over here, And the post-shock region, matter basically tries to, so matter mostly free fall, okay, towards the black hole. And during the free fall, so it's a spherically symmetric infall. Okay, so the gravity itself making the matter to attain this structure. Okay, so so there is no other force which is collimating. It's gravity which is making them free fall, and they look like this kind of thing.
And you said spherical symmetric, but that's in the small scale, you mean, because in the large scale, this is
cylindrical. Yeah, of course. I mean, just in this region, in this thick, high dense region. So here, the force is comparable. The gravity and centrifugal force is roughly comparable. Okay, and matter has nearly stopped over here, and then they are again started their acceleration. So nearly from zero velocity to very high velocity close to the black hole, it is accelerating in near free fall, yeah, sense. Hydrodynamics. Yes.
And what kind of scales?
So gm by c square unit. So this x-axis goes from 2.2 Schwarzschild metric. Schwarzschild metric. So gm by c square is the length scale. Yeah, gm by c square. So the radial domain is from 2.2. So 2 gm by c square is the horizon. So 2.2 gm by c square to 150 gm by c square is the total radial length scale for this case. So this is our in-house. So we develop. So we develop these things.
How does it matter that these scales that it's thick disk or not? I mean, because the accretion scale is much larger.
So the thick disk definition, we say that at any radius, the height of the disk is of the order of r. Okay, so here, for example, you can see that this radius, the height of the disk, though this is 150, height of the disk is around 50 or so. Okay, so it's of the order of, okay, but as you move, I mean, the height doesn't change, so the disk remains thick. Okay, so thickness is there for us.
That's the
thin, right. But yeah, the thin disk, the Sakura-Shinev type thin disk is also possible to simulate from this case by tuning certain parameters. The parameters are viscosity and cooling. Okay, so by enhancing magnetic activity or by explicitly introducing some viscosity parameter, alpha p type viscosity parameter, and significant amount of cooling, because that's what will give rise to black body emission. Okay, so sigma t to the power 4 cooling and viscosity, if we introduce on this disk, then this disk will naturally show me formation of this Sakura-Shinev type thin disk. Okay, so tuning parameters is the thing that we can do in these cases. Okay, we can simulate that thing, but in that case, what we have to do is that the accretion rate we have to play with. So accretion rate, maybe we have to increase. So I don't know if I'm showing. So there are some cases where we have simulated the bolometric luminosity for this disk. So recently we published a paper where we simulated for AGN M87. So M87 has typically 10 to the power 41 arc per second. So some accretion rate actually gives rise to this 10 to the power 14 arc per second. But then if we tune the accretion rate parameter, then the accretion, this radiative efficiency will change. Okay, so by tuning that, we can definitely reproduce the variability, the outburst, and also the spectrum will come out. I'll show the spectrum for some of the cases later. Okay. So yeah, so as I said, if we tune the parameters, then from this thick disk we can go to thin disk, and automatically the radiative efficiency and spectrum will automatically change. So we do not need to additionally invoke thin disk approximation, but the parameters here, the cooling, viscosity, yeah, this model, yeah, definitely, yeah, just by changing some physically measurable parameter, accretion rate. Okay, viscosity is not measurable, but viscosity intuitively we can talk about. See. Yes, very high state means you are extremely soft state, right? Yeah, soft state means Sakura have this generation from this. Sakura have this, if you can generate, then it will automatically be highly high soft state. So very high, what is the disk model that they invoke in very high state? A slim disk. Slim disk can also be modeled, I believe. Okay, by tuning some parameters, slim disk can also be modeled. Advection becomes important. So these are all advective disks. I mean, most of the case, yeah. Yeah, right. And then the increase and advection is there. Yeah. So in that case, so that I have not explored that. Sakura Shunai we have reproduced, but slim disk we did not reproduce. But I think that can also be reproduced. I hope. We just need to see which parameter can do that. Okay. So here is another simulation of accretion onto a rotating black hole, black hole spin 0.95, and we also see the similar type of corona formation or the denser region formation, and then they are also highly variable. So in this case, we have simulated co-rotating disk. So where the or aligned disk, co-rotating and aligned. So spin of disk and spin of black hole, they are both aligned, and the disk, the corona part or the high density part is highly variable. So these are all the hydrodynamic simulation. And what about the radiative properties? So the radiative properties we can extract by doing some sort of coupling between the hydrodynamics or MHD with the Monte Carlo based radiative transfer, and this was my PhD thesis. And we are also still continuing this thing, coupling, so we have previously shown that if the disk becomes highly dynamic close to the black hole, then the spectrum also dances. Okay, so spectral variability, the timing feature. So this is the synthetic light curve, simulated light curve that we generated for one particular type of disk simulation. So light curve can be generated, and from those light curves we can perform. So these are different type of light curves by changing different accretion parameters, tuning parameters, and then we can perform timing analysis, and we can reproduce some cases the FFT, so the low frequency quasi periodic oscillations that I showed you in the beginning slide. So there are several cases where you got 10 hertz, 12 hertz frequencies, and by tuning the accretion rate parameters, the spectral state can also be changed. So from somewhat soft state to somewhat hard state can be reproduced by tuning parameters. So this shows the time variability of the spectral slope. Spectral slope actually varies from hard to the soft range in these cases I have shown. Okay, so with this I end my talk here. So these are the ongoing work which are being happening in my group. So we are basically focusing on the Monte Carlo based radiative transfer. We are trying to improve it. So ray tracing in the background metric. So this, if we are using the Kurzschild metric or Baer-Lindquist curve metric, then we should have a ray tracing mechanism so that we can track the photons, extract out their timing information, so that lag, hard lag or soft lag, this information we can address. The spectrum can be red shift or the blue shift, those kind of effect we can see. We are also trying to develop capability of tracking the polarization through Stokes parameter, and Shoykot is working on that front. The image of the disk can also be generated by this kind of ray tracing. So one single simulation framework where the fluid dynamics will go on at the same time, their image, their polarization, their spectral timing properties, all these things should come out. And on the generativistic fluid dynamics front, we are basically working on doing the GR MHD and GR HD on geodesicness. We have already done MHD and HD, not non-GR on geodesics while working in my postdoc group, but we are trying to extend those for GRMHD, and our goal will be to do simulation of misaligned disk so that we can see the lens threading precision and all those things which we study in GR course. So those things we should be able to simulate on these things. Okay, so with this, I thank for your attention.
Okay, questions?
Only through accretion disk, yes. So yeah, you are correct. So so the jet which is getting out from here, okay, if you can see some arrow, some of the arrows are actually getting out from the simulation domain. Okay, so these matter, there is a high chance that they will fall back. Okay, so these matter can also fall back. Now look at the length scale. This is only 250 Schwarzschild radius. So when you talk about the accretion disk, that the it is coming from a star. So typically for X-ray binaries, the typical distance between the compact object and the center of the star is like 10 to the power 6 Rg, 10 to the power 6 Schwarzschild radius. And here you are seeing only 100 Schwarzschild radius. So from that star, matter has already traveled quite a long distance. And we are simulating only very region very close to the accretion disk. So so the matter that you are seeing here has long left that, and additionally, so that infalling matter and additionally the jet fallback matter from close region can actually will contribute to this total variability or whatever we are seeing over here. So yeah, fallback process is natural. I mean, it will happen just like that. So in small scale, so for example, in these cases, so some of the matter, actually I don't know if I have any. So we see the formation of vortex. Okay, so if there is a vortex over here, then it's basically rotating matter. So velocity vector actually show some rotating fluid. So in the rotating fluid is nothing but some matter is getting out from here, they are rotating and coming back over here also. So that is what is nothing, that is the fallback. We do not explicitly need to introduce any term. It automatically happens. If it has to happen, then it will happen. Okay.
Other questions?
So for your jet fluids problem, how do you decide like the different distinguish between the role of magnetic field and radiation pressure? Because it's like stuff even.
Yeah, so in these simulations, all the effects are actually mixed. So we I mean, if we have to extract information, then we have to see from the equation itself what is the, let's say, radiation pressure term. So in the momentum conservation equation, we are inserting some radiation pressure, so we can calculate explicitly what is the radiation pressure, and then magnetic tension force, or let's say magnetic pressure gradient force. So magnetic pressure gradient force and the magnetic tension force are the contribution from magnetic field, and the radiation pressure term is the contribution for radiation pressure. So those force terms can be compared, and we can say that which is dominating and which is not. So this is the only way we can extract information from the simulation like that. So here